Good day. In this chapter, we'll be talking about nuclear chemistry, the reactions that unstable nuclei undergo, and the applications of nuclear reactions and radiation. The study of nuclear reactions constitutes the field of nuclear chemistry, a subdiscipline of chemistry that explores the properties and reactivity of radioactive atoms. Nuclear reactions are different from other chemical reactions discussed so far because they result in fundamental changes in the identity of the elements involved. The strong nuclear force is the fundamental force of nature that keeps nucleons together in the nuclei. The nucleons are the protons and neutrons inside the nucleus. The binding energy, Be, is the energy that would be released when the free nucleons combine to form nucleus of an atom. It is also the energy needed to split the nucleus into free nucleons. In the stellar nuclear synthesis, the reactions lead to the formation of elements with atomic number smaller than 26 were formed in stars like our Sun, and the energy released during those reactions fuels the stars. Heavy elements than atomic number 26 were created as those stars collapsed and eventually exploded as supernovas. The energy released during these nuclear synthesis reactions represents the energy that holds the nucleus together and can be calculated from Einstein's equation. Binding energy equals delta M times c squared. Delta M is the mass defect, which is the difference between the mass of the nucleus, the atomic mass minus the electrons, and the mass of the individual protons and neutrons in the nucleus. The unit for the mass defect is kilogram. C is the speed of light. Because of the magnitude of c, a small difference in mass translates into a significant amount of energy. Note that the units for binding energy, Be, is joules. As an example, consider the mass defect for a helium nucleus. The atomic mass for helium-4 nucleus is listed over here. It's 6.64465 times 10 raised to negative 27th kilogram. The helium nucleus contains 2 protons and 2 neutrons. The mass of the individual protons and neutrons are provided in this table. The sum of the masses of the individual particles, that is the 2 protons and 2 neutrons, is 6.69510 times 10 raised to negative 27th. The difference between the mass of the particles and the mass of the helium-4 nucleus is 5.045 times 10 raised to negative 29th kilogram. When multiplied by c squared, this equals 4.534 times 10 raised to negative 12th joule, and converted to kilojoule per mole, it would be 2.373 times 10 raised to 9th kilojoule per mole. This is an enormous amount of energy. For comparison, consider that the dissociation energy for the covalent bond in H2 molecules. That energy is only 436 kilojoule per mole. This is 5 million times smaller than the binding energy of a helium nucleus. We can compare the relative stability of the nuclei based on their binding energies. Using the calculations similar to those presented previously, we can calculate the total amount of energy involved from the mass defect of each nucleus. Since the mass defect will naturally be larger as the number of nucleons increases, we typically normalize the total binding energy by dividing the number of nuclear particles in each nucleus. For example, the binding energy of the calculated previously for the helium nucleus would be divided by 4. The binding energy calculated for nickel-60 nucleus would be divided by 60 because there would be 60 nucleons inside that nucleus. If we plot the normalized binding energy versus the mass number, we obtain the plot shown in this figure listed over here. From the binding energy plot, we can make sense of the stellar nuclear synthesis. Stars are fueled by energy released when lighter nuclei fuse to form heavier nuclei, but only as long as the heavier nuclei are more stable than the lighter ones. As you can see over here, the most stable element is number 26, iron. If the nuclei are lighter than iron 56, which has atomic number 26, then they can release energy in the fusion reaction. The formation of nuclei heavier than iron 56 consumes energy rather than releasing it. For this very reason, stars with an iron core starts to die out because they have run out of lighter elements that constitute a stellar field. The most important piece of information you should obtain from this slide is that iron 56 is the most stable nucleus. If we examine the periodic table, we see that the atomic masses of elements are about 2 times their atomic number. In other words, lighter elements in the periodic table typically have equal number of protons and neutrons. However, with increasing atomic number, the ratio of neutrons to protons gradually increase. The purple line you see over here represents the neutron to proton ratio of 1:1. The orange-brown region, as circled orange-brown region, represents the neutron to proton configuration of all known nuclei, while the green dots represents you look at the green dots, those green dots represent nuclides having combination of neutrons and the protons that are stable. The green dots running diagonally through the graph are known as the band of stability. Note that the elements with atomic numbers smaller than 20 in this region, the neutron to proton ratio is almost 1:1. And when we gradually increase the atomic number and the ratio of neutron to proton will be 1.5 to 1. And you might have noticed after 82, after atomic number greater than 82, there are no green dots. Please note the green dots represent nuclei having combination of neutrons and protons that are stable. So this means starting from atomic number 83 and up, the nuclei are not stable. Nuclear reactions are different from other chemical reactions discussed so far because they result in the fundamental change in the identity of the elements involved. In the chemical reaction, there is no change of the elemental identity. A carbon will stay as a carbon before and after the reaction. However, in a nuclear reaction, one element can be changed into a different element. To sum it up, a nuclear reaction is a process that alters the number of neutrons and protons in the nucleus of an atom, and therefore changes the identity of that nucleus. An unstable nucleus that undergoes spontaneous radioactive decay is called a radionuclide. We define radioactive decay as the spontaneous disintegration of an unstable nucleus, accompanied by the release of radiation such as alpha particles, beta particles, positrons, etc. The mode of radioactive decay depends on whether or not the radionuclide is above or below the band of stability. Nuclides that are above the band of stability are neutron-rich and will undergo beta decay. This is quite important. I'm going to say it for one more time. The nuclides that are above the band of stability are neutron-rich and will undergo beta decay, which is a process that converts a neutron to a proton. An example of this process is shown in which a neutron is converted to a proton by release a high-energy electron called a beta particle. Beta particle is the same as an electron. It's also noted as beta subscript -1, which indicates the charge, 0, that's the mass number for an electron. Beta particle can also be indicated as the same as an electron. For example, a carbon-14 nucleus contains 8 neutrons and 6 protons, having a neutron-proton ratio greater than 1:1, which places it above the band of stability. This neutron-rich nucleus undergoes beta decay, as illustrated, to yield nitrogen-14, which has 7 protons and 7 neutrons. At the same time, it releases a beta particle, or an electron. Note the conservation of mass and charge in the nuclear reaction. The total mass of the particles on both sides of the nuclear reaction is represented by the superscripts. On the left side, we have a 14 total. On the right side, it's 14 plus 0. The sum of the superscripts on both sides are the same. It's also true for the subscripts, or the number of protons. For the left side, you have 6 as the sum. The right side, it's 7 protons plus a charge. Remember, for beta particle, the subscript does not represent the number of protons. Beta particles, the subscript represents the charge. So the sum for the subscript on the right side is 7 plus -1. That's also 6. That's how a nuclear reaction is balanced. We make sure both the sum of the subscripts and the superscripts on both sides are exactly the same. In contrast, nuclides that are below the band of stability are neutron-poor, or have too many protons. To achieve a stable configuration, they must decrease the number of protons and increase the number of neutrons. This can be done by positron emission, the spontaneous emission of a positron from the nucleus. A positron is a particle having the same mass as an electron, but with a positive charge. The net result of positron emission is the conversion of a proton to neutron. This is totally opposite to the beta emission, which converts a neutron to a proton. As an example, consider the decay of carbon-11. It has 6 protons, but only 5 neutrons. For this reason, the neutron and the proton ratio is smaller than 1:1. Note again the conservation of the mass and charge in the nuclear reaction. Please also pay attention to the isotope notation for positron. Many times it's written as E0 as the superscript and the +1 as the subscript to indicate the positive charge. So we can also write it as E +1. Basically, a positron is a positively charged electron. This example shows us the nuclides that are below the band of stability are neutron-poor, and this will undergo the positron emission to achieve more stable formation of more stable atoms. Positrons belong to a group of subatomic particles called antimatter, or particles that have the same mass but opposite charge of particles typically found in atoms. For example, similar to positrons versus electrons, protons with negative charge, they are called antiprotons. So for this reason, positrons and antiprotons, they are so-called antimatter. The collision of particles of matter with their antimatter opposites results in very energetic reactions in which the two particles annihilate each other. All the mass of the particle is converted in the energy in this process of the collision between a particle and antiparticle. The amount of energy associated with the annihilation reaction can be calculated from Einstein's equation E equals delta M times c squared, in which all the mass is converted to energy. This energy is released in the form of gamma rays, a highly energetic electromagnetic wave. For example, a beta particle or an electron on the right side and the positron, when they collide with each other, it generates huge amount of energy in the form of gamma rays, as you see in this whole process. Electron capture is another mode of decay by which a neutron-poor nucleus draws in a surrounding electron and converts a proton to a neutron. In this case, an electron in the low energy orbital is captured by the nucleus and reacts with the proton to convert it to a neutron. So a proton reacting with an electron gives you a neutron. As you can see, the nuclear reaction is balanced because the superscripts added together is the same on both sides. Same for the subscripts. 1 plus -1 gives you 0. As an example, consider the electron capture reaction for carbon-11, which yields a boron-11 nuclide in this process after it captures one electron. The nuclear reaction for this process is represented over here. 6 protons plus -1 charge, it gives us 5, which is the atomic number for boron. Superscript 11 plus 0 gives you 11 total for boron. The known isotopes of carbon are presented in table listed over here. Note that carbon-12 and carbon-13, these are naturally occurring carbon elements, and they are isotopes. Their relative natural abundance are known as shown over here. If you can recall, these natural abundances are used to calculate the average atomic mass for carbon in the periodic table. The other carbon isotopes are unstable, as you see over here, and they undergo nuclear reactions with different modes of decay, as you see in this table. And they have different half-life, some with very long half-life, like a carbon-14, and some with very short half-lives. and we will discuss the kinetics of radioactive decay later on. Another look at the band of the stability reveals that there are no green dots with atomic number greater than 83. This implies that elements heavier than bismuth are not stable. We cannot predict if they lie above or below the band of stability because they are not stable nuclei. So we cannot use those stable nuclei as a reference because there are no stable nuclei above atomic number 83. In order to obtain a neutron-proton configuration within the band of stability, these heavy nuclei must shed extra nuclear particles quickly. They accomplish this by the way of alpha decay, which is the spontaneous emission of alpha particle, which contains 2 neutrons and 2 protons. Alpha particles can be noted as alpha with 2 neutrons, 2 protons, so that mass number is number 4. It can also be written as a helium because 2 protons is the helium. And the 2+ charge is usually omitted in the nucleus reaction because we are focused on the nucleus but not the electrons. So for this reason, the 2+ is omitted. Please note uranium-238 will undergo alpha decay or alpha emission. This gives you thorium-234 and an alpha particle. Please also note the product. When you look at the product thorium, this is still above the band of stability. It will also undergo alpha decay in order to get closer to the band of stability. Remember, the whole goal for the nuclear reaction is to arrive at the most stable state. To summarize the most likely decay modes illustrated in this figure, radionuclides that have atomic number greater than 83 and are beyond the band of stability will tend to undergo alpha decay to shed extra particles to get down to the band of stability. Radionuclides that are neutron-rich and lie below the band of stability will tend to undergo beta decay, converting a neutron to proton. Radionuclides that are neutron-poor and lie below the band of stability will tend to convert a proton to neutron, either by electron capture or positron emission. Let's emphasize this for one more time. For the isotopes with atomic number greater than 83, as you see, these nuclides or radionuclides have atomic number greater than 83, and they are also beyond the band of stability. They will undergo alpha decay to go to more stable isotopes, and they can get down to the band of stability. And for the radionuclides that are neutron-rich and lie above the band of stability will tend to undergo beta decay and go to the band of stability. For the radionuclides that are neutron-poor and lie below the band of stability, which is indicated by this circled isotope over here, the nuclides that are below this band of stability and are neutron-poor, they tend to convert the protons to neutron by either capture one electron or do the positron emission. Let's look at one example. Uranium-188 is formed by the decay of tungsten-188. Write the balanced equation describing the decay process. Why doesn't tungsten 188, decay by electron capture, or positron emission. So we are given the initial nuclide tungsten 188 and the product, or so-called daughter nuclide, radium 188. And we are asked to write a balanced nuclear equation by the decay reaction. Given the initial and the final nuclides, we can write a balanced nuclear reaction by observing the principle of conservation of mass and the charge. And in other words, we look at the sum of the superscripts on the left side and right side. They must be equal. Same is true for the subscripts. So here's the equation we write. We start with tungsten 188, and we give radium 188. The number 74 can be determined by looking it up in the periodic table. We can also look up radium will have atomic number of 75. So after you do that, we'll find out you need a subscript of -1. So the subscript will add up to be the same for both sides. Similar thing can be done, so we do know the subscript for the unknown small particle will be 0. A particle carries 0 mass number, and the -1 charge will be the beta particle. So this predicted the mode of decay would be beta decay. Tungsten 188 undergoes beta emission. The equation is balanced based on the conservation of the mass and charge. Please note the neutron and the proton ratio for tungsten 144 is actually 114 divided by 74, which is 1.54 to 1. This is above the neutron-proton ratio, indicating that the nuclei is neutron-rich, in which case the predicted mode of decay would be beta decay. The reason is because in the beta decay, a neutron is converted to a proton, so you will have less neutron. As indicated for the beta decay of uranium-238, the product thorium is still unstable and must undergo additional radioactive decay before a stable nuclide is formed. This is typical of many heavy nuclides that must undergo a series of radioactive decays to achieve stability. An example of a radioactive decay series is illustrated here for the decay of uranium-238. As illustrated previously, it undergoes alpha decay to produce thorium-234, and alpha decay results in a decrease in the number of neutrons by 2 and a decrease in the number of protons by 2. And on the graph, the alpha decay is indicated by the arrow slanting down, decrease in the neutrons, and to the left, that means decrease in the protons. The product of thorium-234 undergoes beta emission. This results in the conversion of a neutron to proton, as is indicated as the graph, as this whole thing moving to the right by 1, because it increases in the atomic number or increase in the number of protons. After a series of decays, it eventually reaches the most stable nucleus, that is lead-206. All in all, uranium-238 and its product radionuclides will undergo a total of 8 alpha emissions and 6 beta emissions before achieving the stable nucleus, which is lead-206. The earliest studies of radioactive substances detected the radioactivity using the photographic plates. This method is still used today. People working with radioactive wear film badges that contain photographic film that fogged up when it's exposed to radiation. Another detection method is the scintillation counters. Compounds called phosphors absorb energy released during the radioactive decay and then release the energy as visible light that can be detected by a photodetector. The greater amount of the radiation, the more intense the light emitted by the phosphor-containing substance. Radioactivity can also be measured using Geiger counters or Geiger-Müller counters, GM counter, which detect the common products of radioactivity, for example, alpha, beta, gamma, based on their ability to ionize gaseous atoms, typically argon. As illustrated in this figure, energetic particles from the radioactive decay enters the Geiger counter cylinder. Once inside, the alpha and the beta particles ionize the argon gas. The ions formed can then migrate to the positively charged electrode. So these are ionized. They'll migrate to the positively charged end, which produces a current. Then we can detect this current and quantify the radioactivity level. When we report the levels of radioactivity, we use units related to the number of decay events. The two most common units are the becquerel, BQ, named after Henri Becquerel, the French scientist who discovered the radioactivity in 1896, which is equivalent to 1 decay per second. Another common unit is Curie, CI, named after Marie Curie and Pierre Curie, which is equal to 3.7 times 10 raised to 10th becquerel. Both these units provide a measure of the rate of decay, which can be used to determine the amount of radionuclides in a sample based on the kinetics. Remember, from first order kinetics, the rate equals K times the concentration R, where K is the rate constant and the R is the concentration of the reactant. In terms of the radioactive decay, the rate is proportional to the radioactivity, A. And we use the quantity of radionuclide N rather than concentration. Since it's the first order process, the decay constant, K, is related to the half-life as demonstrated previously in chemical kinetics. And the half-life for a first-order reaction is always 0.693 over K. Thus, if we can measure the level of radioactivity and we know the half-life of the radionuclide involved, we can determine the amount of substance that is present in a given sample. Please note, all radioactive decay is the first order in kinetics. It will have a characteristic half-life, which is defined as T a half is 0.693 over K. The half-life is defined as the amount of time required for the quantity of radioactive nuclides to decrease by half. As you would expect it, the faster the rate of decay, the shorter the half-life. This concept is illustrated in this figure listed on your right side. If we start with 40 radionuclides, after one half-life, only 20 is left. After 2 half-lives, this has been reduced by another factor of 2, or you only have 10 left. After 3 half-lives, only 5 will remain. The number of half-lives that have passed, N, can be calculated by the time has passed T over the half-life. The fraction of radionuclides that remain can be calculated by the number of nuclei at time t and at the initial time. This will be a half raised to the number of half-lives that have passed. Since n is t over t a half, so we substitute this number in, we have a new equation that is used to calculate the fraction of radionuclides that remains, which is a half raised to t over t half time. Let's look at one example. Radioactive radon 222 decays with the loss of one alpha particle. The half-life is 3.82 days. What percentage of the radon in a sealed vial would remain after 7 days? So in this case, we are given the half-life of radon, T half, is 3.82 days, and asked to calculate the percentage of the radon that would remain after 7 days. From the specified time and the half-time, we can calculate the number of half-lives involved, which is n, that is t over half-life. Then we can calculate the fraction of the radon that remains. So we solve this problem. First, we find the number of half-time it passed. The time that has passed divided by half-time, 7 divided by 3.82. That's 1.83 half-lives that have passed. So the fraction that is left or remains is a half raised to the number of half-lives. This gives us 0.281, which is 28.1%. The answer does make sense because 7 days is a little bit less than 2 half-lives. After 1 half-life, we would have 50% remaining. After 2 half-lives, we would have 28% remaining. So our answer, 28.1%, does make sense. We just learned how to calculate the fraction of the nuclide that remains after a certain time by calculating how many half-lives have passed. So if we know what fraction of the sample is left, or we know nt over n0, and we also know this half-life, then we can calculate how much time has elapsed. And this is the mathematical foundation for the radiometric dating, such as carbon-14 dating. Carbon-14 is formed in the upper atmosphere by reaction of the cosmic radiation with atmospheric gases. The carbon-14 then combines with oxygen to form carbon dioxide, which is incorporated into the living plants via their photosynthesis. As long as the plant is alive, the relative amount of carbon-14 remains stable as the plant continues to take in atmospheric carbon dioxide, which contains small amount of carbon-14. When the plant dies, it no longer takes in carbon dioxide. So the carbon-14 starts to decay, and the carbon-14 to carbon-12 ratio will decrease because carbon-12 remains constant. We can use the change in the carbon-14 and the carbon-12 ratio to estimate the age of the item using the half-life relationship, and this is so-called carbon-14 dating. Let's look at a real-life example. A mammoth tusk containing grooves made by a sharp stone edge was uncovered at an ancient campsite in the Ural Mountains in 2001. The carbon-14 and carbon-12 ratio in the tusk was only 1.19%. That is as that of in modern elephant tusks. How old is the mammoth tusk? So in this example, what we know is that the carbon 14 and 12 ratio is only 1.19% compared to a living sample from modern elephant. We also know that the half-life of carbon 14 is 5,730 years. We are asked to estimate the age of the mammoth tusk. So knowing this fraction and the half-life, we can use the half-life equation to calculate how much time has passed by. And T equals negative half-life over 0.693 times the natural log of the fraction of the radionuclide. We substitute the half-life in and the fraction in. We find out it's 3.66 times 10 raised to 4 years. The calculated age of the mammoth tusk, about 40,000 years, makes sense historically. Since mammoths walked the earth during the last ice age, we estimate that it would take more than 6 half-lives to decrease to 1%. This estimate is consistent with our calculated answer. The accuracy of radiocarbon dating can be checked by determining the carbon-14 content of the annual growth rates of very old trees, such as Bristol cone pines in the American Southwest. When the radiocarbon ages are plotted versus the actual ages obtained by counting the rings, there are discrepancies. Some of these discrepancies can be explained by the fact that the intensity of cosmic radiation changes, so the production of carbon-14 in the upper atmosphere can vary over time. Then corrections are made for these variations, and careful analytical techniques are used to avoid contamination. Radiocarbon dating can produce results that are accurate to plus or minus 40 years for samples that are 500 to 50,000 years old. The biological impact of radiation depends on how much of it is absorbed by an organism and the type of radioactive particles involved. Because the biological effects depend on multiple factors, we use different units to describe the level of exposure to radiation and to determine the effect it may have on an organism. For this reason, the relative biological effectiveness, or RBE, have been established, as you can see in this table. The alpha particles, beta particles, gamma rays, neutrons, and protons, they have different relative biological effectiveness. The gamma rays and the beta alpha particles produced by radioactive decay have enough energy to break chemical bonds and produce ions and free electrons. For these reasons, they are often referred to as ionizing radiation. Ionization of matter in living tissue can lead to radiation sickness, birth defects, cancer, and so on. Units for expressing quantities of ionizing radiation are summarized in this table. The sievert provides the measure of the amount of tissue damage. The relative biological effectiveness, or RBE, is inversely proportional to the penetrating power of the radiation. Alpha particles are massive compared to other types of radiation. Remember, alpha particles have 2 protons and neutrons, and the mass number is 4. It's much heavier than beta particles or an electron. As a result, they cannot penetrate very far because they collide with atoms and molecules in their path, and they can be stopped by a piece of paper. or the top layer of the skin. Because they are so large, they can do considerable damage to tissue and have an RBE value of 20. Smaller particles that might be produced during nuclear reactions include neutrons and protons. While not as massive as the alpha particle, they have considerable mass. The neutron has an RBE value between 3 and 5, while the proton has slightly higher RBE value of 10. And the beta particles, essentially, they are the high-energy electrons. They have a very little mass. As a result, they can penetrate farther than alpha particles or protons or neutrons. They can pass through paper, but can be stopped by a thin piece of aluminum. Beta particles have an RBE value between 1 and 1.5. Gamma rays have no mass and so have the highest penetrating power. They have the lowest RBE value of 1.0. The gamma rays can be stopped by a thick layer of lead. When considering the threat to biological tissue, one must consider both the type of radiation and its penetrating power. Alpha rays are very dangerous if ingested because they have the ionizing power, but are not a serious threat if the source is outside the body. Gamma rays are the most dangerous if the source is outside the body because they have a high penetrating power and can travel large distances before interacting with the tissue. The effects of exposure to different levels of radiation are summarized in this table, excerpted on the left side. At low doses, the immediate effects are minimal, although there may be carcinogenic and mutagenic damage to DNA. As the dosage level increases, more severe biological effects are experienced, including a temporary reduction in white blood cell count. Radiation sickness. At levels higher than 2 sieverts, the intensity of radiation sickness increases, leading to intestinal bleeding, bone marrow destruction. At levels above 4 sieverts, death usually occurs within weeks by infection or within hours at a very high dosage. When evaluating the risks from radiation, we must consider radiation from both natural and other sources. The threat from radon gas depends on the geology of the region. This figure provides an estimate of the amount of radon gas in soils throughout the country. Note that the highest levels are found in the northern Appalachian regions, in the upper Midwest, and the Plains states. The concentrations of radon gas will depend on the amount present in the subsoils and on how gas tight the building foundations are. The US EPA has established a limit for how much radon can exist without hurting the health, meaning that the people occupying the buildings with concentrations above the designated level should take remedial actions to minimize their exposure to radon gas. Radioactivity can be used in the radiotherapy, and this table summarizes some of the radionuclides used in therapeutic applications. Because of the ionizing radiation causes most damage to cells that grow and divide rapidly, it's a powerful tool in the fight against cancer. Radiation therapy consists of exposing cancerous tissues to gamma radiation. Sometimes the radiation source is external to the patient, but it can be surgically implanted into a cancerous tumor. Sometimes a nuclide's chemical properties can be used to its advantage. For example, iodine, 131, is concentrated in the thyroid gland and can be used effectively against thyroid cancer. Unfortunately, radiation destroys both cancerous cells and healthy cells, so patients receiving radiation therapy often suffer from radiation sickness, including hair loss. This table summarizes some of the radionuclides used in the diagnostic applications. The movement of nuclides throughout the body and their accumulation in certain organs provide ways to assess the organ function. Another example of a diagnostic radiation technique is the positron emission technology, or PET. PET uses short-lived neutron-poor positron-emitting isotopes such as carbon-11, oxygen-15, fluorine-18, which have been incorporated into other compounds such as glucose. The rate at which the glucose is metabolized in various regions of the brain will produce different levels of glucose in the brain cells, which can be detected as isotopes decay and emit positrons. The emitted positrons react via the matter-antimatter reactions to produce the gamma rays, which are detected as they exit the brain. In this figure, we have two PET scans. The brain scan on the left side represents a healthy functioning organ. Red and yellow indicate high levels of brain activity. The brain scan on the right side with dark blue and black regions indicate the low brain activity in a person suffering Alzheimer's disease. When an atom of uranium-235 captures a neutron, it creates a highly unstable nucleus which spontaneously splits into two lighter nuclei in a process that is called nuclear fission, which means a heavier nuclei splits into two lighter nuclei. There are other pathways for the uranium-235 fission reactions, as you can see over here. Note also that the reactions are balanced based on the conservation of mass and charge, which means the sum of the superscripts on the left and the right are equal. So it's also true for the subscripts. All of the fission reactions in this slide, they produce multiple number of neutrons. All the reactions also result in a mass defect. The products will have less total mass than the reactants. The decrease in the mass is released as energy according to Einstein's equation E equals delta M times C squared. The process of self-sustaining or self-amplifying fission reaction is illustrated in this figure. In the first step, uranium-235 nucleus captures a neutron, leading to additional fission reactions in which more neutrons are generated. And these neutrons can be used to generate more subsequent fission reactions. All the fission reactions on the previous slides produces multiple neutrons, as you can see over here. And this can be used to initiate more fission reactions. This series of subsequent fission reaction is called the chain reaction. The minimum amount of fissionable material that is needed to sustain a chain reaction is called the critical mass. And uranium-235 is the most abundant fissionable nucleus, but it constitutes only 0.72% of the uranium in naturally occurring uranium minerals, such as pitchblende. In order to achieve the 3% to 4% concentration of uranium-235 for the sustainable reaction in nuclear reactors, the uranium-238 must be enriched using the extraction and centrifugation techniques. Enrichment to 85% is needed for nuclear weapons. Another fissionable material used in the nuclear reactor is plutonium-239. When plutonium-239 is mixed up with uranium-238, some of the neutrons produced by fission are used to initiate and maintain the fission chain reaction involving plutonium-239. Some of the neutrons, however, react with uranium-239 to produce more plutonium-239. This type of reactor is called the breeder reactor because it breeds its own fuel for future use. A typical nuclear power plant configuration is illustrated in this figure. The reactor core contains fuel rods, which consist of the enriched uranium. Control rods containing boron and/or cadmium can be inserted to absorb some of the neutrons and prevent the chain reaction from running out of control. The fission chain reaction generates a significant amount of energy in the form of heat, which is used to convert water to steam. The steam then flows through a steam turbine generator to produce electricity. The steam is then cooled and condensed back to liquid water and recycled through the system. The energy of the sun is derived from high-speed collisions and combinations of hydrogen nuclei to form helium. These nuclear reactions, in which the small nuclei and/or subatomic particles collide and fuse to form a more massive nuclei, are called the nuclear fusion. The simplest example of a fusion is the reaction shown on the slide, and this represents one of the many fusion reactions that occurs during the primordial nuclear synthesis, in which you have smaller particles combined to make a bigger one. This fusion reaction also releases substantial amount of energy. Another reaction involves the fusion of two deuterium nuclei to form the helium-4. Again, note the conservation of mass and charge in the fusion reaction, or the sum for the subscripts are the same on both sides. It's also true for the superscripts. Other nuclear synthesis reactions that most likely occurred in the early universe are shown on this slide. These reactions produce significant amount of energy and they led to the formation of heavier nuclei. The energy produced by these reactions contributed to the kinetic energy of nuclei formed, so the rate of collisions and fusion reactions continued. Note the positrons produced in the first reaction. These positrons can react with electrons via the annihilation reaction to generate additional energy. For decades, scientists and engineers have been investigating the use of fusion reactors for the generation of clean energy. One reactor design is the tokamak, which heats a mixture of deuterium and tritium to temperatures of 1.5 times 10 raised to 8 Kelvin. The temperature is extremely high. At these extreme temperatures, all the atoms are ionized to form an incandescent plasma. The high temperature plasma is contained using a powerful electromagnets. The high-speed collisions between the deuterium and tritium are used to produce helium-4, and neutron is also produced together with a significant amount of energy. The neutrons that are produced collide with lithium nuclei located in the blanket layers around the hydrogen plasma. The lithium undergoes fission to generate more tritium, which can be collected and used as fuel in later reactions. Thus, the configuration represents as a breeder reactor system for the fusion reactors. Among the advantages of fusion as a source of energy is that it does not require large amounts of radioactive materials, and it does not produce large amounts of radioactive waste. Also, deuterium is readily available in enormous quantities in the oceans. All right, that's it for today. Have a good day. See you next time. Bye.